All right, it is 11:10, so let's get started. Welcome to Data 8, lecture number 8. Today we're going to be finishing up what we did not get to finish yesterday, and then we're going to be talking about charts. Some announcements. So as you are very aware, there's still drilling, still jackhammering. So I just ask for your patience, and if you need me to speak up or repeat something, just let me know, okay? Just raise your hand, say something. I don't want you to miss anything, so please just let me know if you need me to repeat anything. I want to remind you that homeworks 1 and 2 are due tonight. If you did not know that before, well, hope you should get going. Homework 3 is also released, and it is due on Friday. We're also going to be releasing Project 1 on Thursday, and there will be some deadlines for that we'll talk about when it gets released. Cool. Any questions about that? All right. So where did we leave off yesterday? We were looking at US. Oh, I do not have my slides. Let's try that. All right. So we're looking at US Census data. We're comparing the years from 2010 to 2015. So the first thing we did was we looked at the populations, the difference in populations from 2010, and compared it to 2015. From looking at the differences in populations, we found that there were a lot more 68-year-olds in 2015. And we found that the reason for that was because of World War II, mostly because of World War II. We were looking at gender ratios in 2015. So before we were comparing populations in different years, now we're looking at population in just a single year, but we're comparing two different groups within that year. We're comparing males to females. We noted that there are more male infants, but more females overall in the population. And that means that although there are more male infants, somewhere along the line, there are more females than males. So let's take a look at why that might be the case or what's going on there. So let's switch to my demo. All right, and there we go. Okay, so I'm going to pull out my US population table. If you'll remember from yesterday, let me make that full screen. You toggle toolbar, toggle header. All right, excellent. So if you remember from yesterday, we were looking at this table here, which contained all the population in every group in 2015. Okay. Now let's take a look at just the females. So to get the females, I can just take my US Pop 2015. And I want to grab only where the sex is 2. All the females and all the ages. But you'll remember that the age 999 is not actually an actual age. So it represents the combination of all ages. Okay, so I don't want to include that in my comparisons, so let's take it out. So I can take .where, and then I can do .where age are not equal to 999. So I had 92 rows emitted here before. When I run it again, I had 91 rows emitted, so I have one less row than before. That behaved like I expected to. So I'm going to call this the females table. Females. All right. Now I can do the same thing to the males. Oops. So all I have to do is change my variable names and change my sex to 1. And now I have a table with the males. So the number of males in 2015 at all the possible ages from 0 to, if you remember, it goes from 0 to 100 because every age after 100 is lumped together in 100. So let's take a look at these tables. All right, so just to confirm, the male column age contains the numbers 1 through 100, and so does the females. But conveniently enough, these two tables have the 2015 column, and that 2015 column has the same number of elements. We can actually compare different corresponding elements from both tables and use them to kind of see what's going on between females and males. Okay, so for example, in 2015 we had about 1.9 million infants, female infants, but we had about 2 million male infants. Okay, so we can take out, I can take the females.column 2015, there are the numbers there, and I can divide by the males.column 2015. And now I have the female to male ratio of every year, of every age, every age going from 0 to 100, okay? So this is an array, and I can put this into a new table so we can take a look at that more closely. So let's put that into a new table. I'm going to call it ratios. Ratios equals table with columns. Okay. And I'm going to include my original age column. So I do want to keep that 0 to 100. So age, females.column age. And I'm going to call this new column the 2015 female to male ratio. Wow, we have like surround sound on the drills. We have drills coming from all different directions. OK. Bear with me. Bear with me. All right, so now we have this new table. What have I got? I have, for every age in 2015, the female to male ratio. Okay, so for example, here we see that there are a little bit less females than males, and like the ratio is about 0.95 to 1. And if I go down to, let's say, age 75, so we noted before that there are more male infants, but in the overall population, there are more female people. So that means that somewhere along the line, the ratio here must flip. It must go to like more females than males for the overall population to have more females, right? So let's try to see if we can confirm what our intuition says. Let's take a look at where the age is above 75. And sure enough, once we get to where ages are above 75, we have significantly more females than males, 1.22 females for every 1 male. Okay. So we have a lot of numbers here. And typically when we have a lot of numbers, we try to use visualizations to try to see like the behavior of all those numbers. We're going to be going into that today. But if I were to just use this function called plot, which I'm going to talk about later today, we can see that when the age is young, when people are young, they're about the same number of females to males. But as people get older and older, suddenly there are a lot more females compared to males. Okay? So interesting behavior of data. We found this out by investigating the female to male ratio in a single year in 2015. And we can see this interesting trend line right here. And we're going to be talking about visualizations today, because this visualization allows us to look at all 100 ages at once and look at the behavior of all 100 ages at once. Whereas before, we were limited to kind of like slicing out parts of the table and looking at that. Okay? Any questions about what we did here? All right, excellent. So let's go back to my slides. I want to start off today with data of the day. Here is a joke from the UC Berkeley Memes for Edgy Teens page. It says, hey, you want to hear a joke? Sure. A job? I don't get it. I know you don't. And then the sad guy. But in reality, the job growth these days hasn't been that bad, as although the UC Berkeley Memes for Edgy Teens page would like you to believe otherwise. May's job growth wasn't bad. It represented the 80th straight month of gains, the longest such streak on records. We've added more than 16 million jobs since the labor market bottomed down in early 2010. So great job market. And we can see from this graph that the number of non-agricultural jobs, the change in the number of agricultural jobs from the prior year has only been positive. So these are only positive numbers, which means that we've only been adding jobs year over year. Okay, so these are the y-axis is in millions of jobs, and here we see the total number of jobs and the private sector jobs plotted side by side. So we can kind of get a sense of how those things are behaving. In particular, it looks like data science jobs are doing pretty well. So this quote from the McKinsey Institute says, the US economy could be short of as many as 250,000 data scientists by 2024. And if I were to plot the number of data science jobs in the top 10 data science employers over time, we find that the number of data science employees is going up pretty quickly, and will probably continue to do so for the next couple of years or so. So we're talking today about data visualizations. Data visualizations are useful because they allow us to see a lot of data at once and make sense of a lot of numbers at the same time. So to get you guys thinking about it, here are some questions for you. Which of the following questions can be answered by this chart? Among survey responders, which proportion did not use their phone for online banking? Use their phone for online banking or to look at real estate listings? Did everyone use their phone for at least one of these activities? And did anyone use their phone for both online banking and real estate? Talk about it with your neighbor. Which questions can I answer and which questions are hard to answer with this chart? You start by saying hello, my name is blank. I wonder what you thought about the first question. It's so interesting. All right, so let's wrap it up. All right, for the first question, which proportion did not use their phones for online banking? How many guys say, yes, I can answer this? OK, so feeling good about that one. What about number 2? What proportion used either for online banking or real estate listings? How many guys think you can answer that? OK, a couple of brave folk. Did everyone use their phone for at least one of these activities? Can we answer that with this chart? OK, and did anyone use their phone for both online banking and real estate? Can you answer that with this chart? All right. Some more brave people. All right, so what proportion did not use their phone for online banking? That one is not too bad. All I have to do is take the number that used their phone for online banking and do 100 minus that, because it's a percent. 100 minus that, I have about 43% of people did not use their phone for online banking. Okay, so I can answer that with this chart. On the other hand, when I try to figure out whether people used online banking or real estate, that's a little bit harder because I'm not sure the proportion of people that did both. I could have had everyone here also did real estate listings, or I could have very few people from online banking did real estate listings. It's kind of hard to tell whether people did one or the other just from this chart alone. Okay. Oops. Whoa. Did everyone use their phone for at least one of these activities? Again, pretty hard to tell because I could have had one person here that didn't fall into any category, or I could have had like these categories. Everyone who did health conditions did not do online banking. I could have had stuff like that going on, so it's hard to tell. Again, can't tell from this chart alone. Now this question, did anyone use their phone for both online banking and real estate? For those of you who said yes, why did you say yes? Chase?
Okay, so this question is kind of abstract, but you can basically, in order for this question to be answered yes, you need to be able to prove that just one person had used their phone. So if you look at, like, take the ideal case where 57% of people do online banking and everyone who doesn't do online banking looks up real estate on their phones. Like if you look at the extreme case, even if that were true, 43% of people don't do online banking and 44% of people look up real estate. That's 1% difference there. That means that 1% of people necessarily did like both.
Yeah, so Chase says, let me try to repeat what she said. So you're saying, let's look at the proportions for both. And when you add them together, we get like 101%. Yeah, so Chase is correct. You can actually tell that there's at least one guy in there, one girl in there who did both online banking and real estate. But that question is pretty hard to answer with this chart. It's not necessarily something that the people who created this chart were trying to get you to understand. So when you're looking at charts and plots and visualizations in general, you should try to keep in mind like what kinds of things, what kind of questions can you answer with this chart? What kinds of questions are hard to answer? Is there any information hidden in the questions that are hard to answer that you think would be more interesting and can be shown with a different visualization? All right, cool. So kind of a warm up, and let's talk a little more about visualizations. Basically, the one principle that we try to obey when it comes to visualizations is the area principle. Areas should be proportional to the values they represent. And the reason for that is just because of the way we perceive things. So we can perceive when things are really big, we perceive them as more important than things that are really small. Okay? But for example, in this case, in 2013, 30% of accidental deaths of males were due to automobile accidents. 20% of accidental deaths of females were due to automobile accidents. But if you look at the way this person constructed this chart, this is probably for females, this is probably for males. And although the lengths of the cars went from 20% to 30%, because the height of the cars also grew in size, this car right here actually has about like twice the area of this car down here. This is pretty misleading. It looks like there's about 2 times as many male accidental deaths because of automobile accidents compared to females. But in reality, it's really about 1.5 times. Okay? So it's a silly example in this case, but you'll see tomorrow when we talk about histograms why it can be easy to oftentimes violate this area principle. So just keep that in mind as we talk more about visualizations. And now I'm going to take attendance. So if you will please take out your laptops or your phones. The URL is, again, sorry, I went really quickly there, bits.ly/@-d8, so @data8. And I'm going to resume collecting responses right now. So again, if you are in row A, please raise your hand. Row A, that's the front row here. OK, so if you're in row E, please raise your hand. Row E, 5 rows behind. Yes, great. If you are in row I, please raise your hand. That's you guys in the back there. OK. If you are in column 1, please raise your hand. Great. Column 5. Count over 1, 2, 3, 4, 5. It looks like we have very few column 5ers. OK. Column 10. Column 10, would you raise your hands just to make sure you guys know where you are? Column 10. OK, yep. So please go ahead and fill out that attendance survey. OK, let's move on. So as mentioned before, visualizations allow us to look at a lot of data at once. Let's find out how that works. Let me close that. OK. So what I'm going to work with today, so let's talk about visualization. We're going to look at actors. OK, so I have a data set here with some famous actors, 50 actors, ordered in the total gross they made from their movies. So I have here one row for Harrison Ford. Harrison Ford made a total gross of $4,871, and this is in millions of dollars. My God, I should have been an actor. So he made a total of like so this is like total of everything. So he made 41 movies, and those 41 movies combined, the box office totals came out to be about like $4.8 billion for Harrison Ford. Wow. So he made an average of so each movie that he made had a box office of about like $118 million, and his #1 movie was Star Wars: The Force Awakens. The gross of that movie was $936 million. Okay, so we have here some actors, the total gross, number of movies that they had, and the average per movie. Let's see if the relationship between the number of movies and the total amount of money that they made, if those two variables have a relationship. Okay, so what I can do there is use what's called a scatter plot. Use a scatter plot. I take my table, and call actor.scatter. And I write what I want to be on the x-axis, number of movies, and then what I want, the variable that I want on the y-axis, total gross. Very simple, and it broke because I forgot an S. There we go. OK, so look at this. I have here total gross on the y-axis, number of movies on the x-axis. Is there some relationship between total gross and number of movies? It's a rhetorical question. You should just think about it. It looks to me like there is, because if I look as the number of movies goes up, the total gross also tends to get higher and higher. Like, for example, this area right here, where once you made 60 movies, it looks like you're making a lot more money than people who've only done like 20 right here. All right? But you would kind of expect that, because like as you make more movies, you make more money overall. Perhaps something more interesting is the average number of dollars actors made per movie. Another scatter plot, and I want to look at the number of movies and compare that to the average per movie. What do I notice here? OK, so it looks to me here that there is that as the number of movies goes up, the average amount of money you make per movie goes down. Why might that be the case? Well, we can take a look. But I first want to point out this little guy all the way up here. So there's this guy who only made like 5 movies or so and made a lot of money per movie. Who is that lucky guy? Let's find out. So I can look at that by going into my table. And it looks like he made about like 5 movies or so. We can take everyone who made number of movies, who made below maybe like 10 movies. And let's see if there's a guy. So our guy's name is Anthony Daniels. He made a lot of movies. He made a lot of money and only 7 movies. And that's because, does anyone know? Does anyone happen to know Anthony Daniels? Yes, name? Sorry? Yes, your name is? Daniel. Oh, yes. So Daniel says Anthony Daniels is C-3PO. Conveniently enough, in all 7 of the Star Wars, so this is from 2015, I believe, in all 7 of the 7 Star Wars movies at the time, and he made a lot of money per movie because the Star Wars movies are pretty successful. So if you want to make it big in the movie industry, be a droid. OK, so let's take a look at the people down here. OK, so it looks like people who made a lot of movies didn't make a lot of money per movie. Whether that's because they were not famous or they just had to do a lot of movies, we can find out by looking at our table. Let's take that. Number of movies are above. And let's take a look at people who did above 60 movies. OK, so 60 movies. And what do we notice here? I don't watch a lot of movies, but even I know these people. So Samuel L. Jackson, Morgan Freeman, Robert De Niro. It looks like these people made a bunch of movies. And it looks like not all their movies were great successes, but the ones that were great successes, well, that's the reason why we all know their names now, right? So it looks like Samuel L. Jackson, The Avengers, The Dark Knight, Meet the Fockers, pretty cool movies. OK, so some interesting stuff we can get just from this one chart. The visualization, looking at this visualization, gives us ideas about what to investigate in the data. OK, so before you're looking at this, you're like, oh, looks like people made money, great. Plotting this lets us say, oh, I wonder what's going on here. I wonder what's going on here. And that lets us see more interesting things about the data that we couldn't do before. OK, so any questions about what we did here? Cool. So now what I want to do is I want to switch data sets. I have here a different data set called top. Instead of having 1 row for every actor, this data set has 1 row for every movie. OK. And I believe this data set contains the top. So this data set contains the top grossing movies of some number of years. We have about 200 movies here, so probably the top 200 grossing movies. And I have here the gross total made from the movie and the gross total adjusted in 2015 dollars. So this was released in 2015. This one released in 2009, so Avatar. So we're going to take a look at this data set and see what we can get out of it. OK. So in this sense, let's take a look. Movies. I don't think this is the table I'm looking at, or I want to look at. Inferential thinking, movies. I believe I actually want to do movies. That's right. That's right. Movies by year. sorry, my bad. This is actually a movie. This is actually a table we're trying to look at. So sorry, before we had one row for every actor. Now we have one row for every year, and we have the highest grossing movie for that year. Okay, so we have 2015. The most grossing movie was Star Wars: The Force Awakens, and The American Sniper in 2014, Catching Fire in 2013. Let's take a look at this table and see if a visualization will tell us anything about the data. Okay, so what I can do is instead of making a scatter plot, I can make what's called a line plot. If I plot the year on the x-axis and the number of movies on the y-axis and connect the dots with a line, then what I see is this. It looks like there are not that many movies. Number of movies. So right here I have the number of movies total released during that year, and what I'm showing here is every year there was some number of movies released. In 1980, not that many. In 1985, not that many. But it looks like overall there have been more and more movies released per year. And in 2015, we had a lot of movies, about 700 of them. Okay. So if I want to look at just perhaps the movies that were released after 2000, I can't zoom into the plot with like a button here. What I have to do is I have to change my data and then replot it again. So to do that, what I want to do is use where, century 21 equals movies.where, and I want to take where the year is above 1999. And if I plot that, so if I do that and then plot it, now I have same plot, but only from the years 2000 to 2015. So 2000 to 2015. You can see here that we have a zoomed in part of the plot. Okay. I can now take the same table that contains the years 2000 to 2015 and look at the total gross. So look at the change in total gross for the highest movie over time. Dot plot year total gross. So not the highest movie, sorry, but the total amount of money raised by the movie industry in that particular year. So in 2000, movie industry didn't do so hot. 2015, they did pretty well. So this right here is, I believe, $11 billion. Okay, so $11 billion total for movies released in 2015. This is not adjusted for inflation, but I could if I wanted to. But overall, the dollar amount of movies raised like year over year looks like it's been increasing a good amount by about maybe like 1.5 times from 2000 to 2015. Any questions about that? Yeah, Luke?
When the year in the table is not in order.
So Luke asks, what happens if the years in my table are not in order? Well, let's find out. So I haven't gone over this method yet, but there is a method I can use called sample. Let me see. So I'm not going to go over into how this works, but basically this is going to shuffle my table. So I have 2008, 2002, 2011. If my table is shuffled and I want to plot it, so let's say I want to plot year total gross, I get the same thing. Okay, so when it reorders everything, you don't have to worry about sorting it in the correct order before you plot it. You can just plot it. Okay, so nice question. Okay, so we can take a look at the year 2009. So if you look at the year 2009, it looks like there were maybe 15 less movies released in 2009 than in 2010. So 15 less movies, but the total gross was higher than in 2010. And that's because of this movie called Avatar that happened to make a lot of money. So if I want to take a look at that movie, I can always do century 21. Where. So if I want to pull out if I want to investigate a single row, all I have to do is do r equal to 2009. Okay, so there's Avatar. Made a lot of money. Cool. So we've looked at so far. So far we've been limiting our kind of data analysis to numerical data. Okay. There are a couple of different types of data. Most visualizations only work on some of the types. There are very few that work on all types of data. Okay, so it pays to kind of understand the different types of data you might work with, and then which visualizations can work with different types of data. Okay, but in general, when you're doing a visualization, you want every value in your column to be the same type and comparable to each other in some way. This sounds pretty obvious, but for example, when we were looking at census data yesterday, in the age column, we had the value 999. Okay, the value 999 is not directly comparable to the value 10 because the value 999 is not an age. It represents a collection of ages. Okay, so you do want to be careful about special values like that. We have numerical data, which we've done right now, where each value is from a fixed scale. Okay, because they're from a fixed scale, numerical measurements are ordered. It makes sense to put like 1 before 10. It makes sense to put 10 before 100. So there's an ordering to them. And the differences between the data are meaningful. So making $20 is twice as good as making $10. Making $100 is 10 times as good as making $10. Okay. On the other hand, we have categorical data. In categorical data, instead of having values from a fixed scale, we have values from a fixed set of values. Okay, so not scale. Sometimes numbers, sometimes strings, sometimes anything, but they're not in like a scale that goes up and down. Categorical data can have an ordering sometimes, but doesn't always have to have an ordering. So for example, the color of t-shirts in this classroom, red, green, yellow, doesn't really have an ordering, but the size of the t-shirts does. So small, medium, and large, that's categorical data, but it does have an ordering because small is smaller than medium, which is smaller than large. Okay. In the case of numerical data, we had meaningful differences between the numbers. In categorical data, you're either in the category or you're not. So small is not necessarily twice as small as medium. Medium is not necessarily twice as small. You're either in the category small or you're not in the category small. It's hard to make a comparison across categories in categorical data. Yeah, Kevin?
On the population chart, would a sex code 0, 1, and 2 also be categorical because numerical arithmetic operations wouldn't make sense on those numbers, right?
Yeah, so that's a great point. So Kevin points out that when we were working with census data, the sex column contained values 0, 1, and 2. Those values are numbers, but we don't consider them numerical data. I'm going to actually have a slide about this later. We don't consider them numerical data because we can't do like the average age or the average sex is like 0 plus 1 plus 2 divided by 3. It doesn't make sense to like do numerical stuff with those numbers because those numbers actually represent categories. So it's categorical data, but in numerical form, but they're still categories. Okay. All right. So let's take a look at some terminology. So as I'm going to work through these visualizations, I just want us to be very clear on the terms and the vocab that we have to know in order for us to communicate with each other. Okay. So first, individuals, this is from before. Variables, so in our case, a variable is typically a column. These columns or these data are features that vary across individuals, variables. Okay? Variables have different values, and those values can be numerical or categorical or other types that we haven't discussed so far. But so we have individuals that have variables, different value variables. The variables have different types. Okay? We use the word distribution as a special type of term that refers to when you, instead of counting the number of individuals, where you kind of group individuals together and look at frequencies. We're going to be looking into that in depth tomorrow when we talk about histograms, but I want you to be aware of the term distribution. For example, there could be 10 small t-shirts, 20 medium t-shirts, 30 large t-shirts in this class. That would be considered a distribution because we're working with counts of different categories. So we've looked at two types of plots so far. We have scatter plots and line plots. We typically use scatter plots. We typically like to use scatter plots generally because they work on a lot of numerical data. When our data are numerical and there's only one value for every value on the x-axis, we use a line plot because the differences between the variables are meaningful. Okay, so criteria for a line plot: only one y value for every x value, and the differences between y values is meaningful. So this is where you use a line plot. Scatter plots are used just to kind of show like comparing two numerical variables together. Okay. Any questions about that, Kevin?
So basically, if the numerical differences are not meaningful, then we use a scatter plot, and if the changes are meaningful, then we use a line graph for it.
Yeah. So Kevin asked. So scatter plot is not meaningful differences. Line plot is meaningful differences. That's more or less correct. You typically kind of want to use your best judgment and say, OK, a line plot here makes sense. For example, in this case, because we're looking at, 2008, a lot more movies were released than in 2009. Okay, so you can directly compare this way and see there's a big drop here. Whereas in a scatter plot, it doesn't really make sense to look at like this average per movie and look at this average per movie and compare. So use your best judgment and kind of use those rules of thumb that I've just mentioned to kind of decide which plot you think is best. OK, let's continue. I'm going to do a demo on categorical data. So now I'm going to take my top table. So first of all, how many of you guys are still taking attendance? Anyone here still working on that form? OK, great. Going to close it. All right, so now let's work with that top table. Sorry for getting that out of order before. I'm going to call this categorical data. All right, so I looked at before, movies. These are the movies that made the highest. These were the highest grossing movies for, it looks like, some large amount of time, so maybe since 1950. And it looks like here we have the highest grossing movie is Star Wars: The Force Awakens, released by Disney in 2015. It made $906 million in the box office. And this is the dollar amount adjusted to 2015 dollars. Okay, so I can look at the top. Let's look at the top 5 movies in this table and use a bar chart to compare them. So I'm going to take top 5, a range 5. Okay, so I have my top 5 movies. And I can use a bar chart to compare them. I can use this method called bar H. The way bar H works is you put the categories first, so the column for the categories first, and then the values for like how tall or long each bar is as a second argument. So title, and I want to compare the gross income made. Okay, so here I have Star Wars: The Force Awakens made this much money, Avatar made that much, Titanic made that much, Jurassic World, etc. Okay. Now do note that this gross here on the x-axis is going from 0 to maybe 1. And that's because when the plot was generated, it automatically kind of does the scientific notation here. So you do have to be aware that this 0.8 is not just $0.8, because that would make the movie business really unlucrative. It actually refers to the fact that you have 0.8 times 10 to the power of 9. That gives you back the original value of the table. All right. Any questions about that? So typically, we like to use this what's called a horizontal bar chart here, because the lengths of the labels of the categories is easier to kind of work with. If I instead wanted to do a vertical bar chart, I might get interesting looking results because the labels are too long. Okay, so pretty long, not that great. Usually, a horizontal bar chart works better. Okay. Cool. All right, and let's take a look at comparing. So let's compare the top 5 movies. But instead of comparing the actual dollar amounts, let's look at the actual dollars amount adjusted for inflation. Okay, so all I have to do there is pick different. All I have to do there is call bar H with, instead of title and gross, gross adjusted. Adjusted. And now we can see that although Titanic made less dollars amount, when adjusted for inflation, Titanic actually made more money than Star Wars and Avatar. Okay, so we can see here the differences between the two. All right, so right now I've looked at. So one thing to note here is I've looked at only the top 5 tables from the top 5 rows from this table. There could have been a movie like kind of down here below that got released a long time ago, like in 1960. That didn't make a whole lot of gross money, so it didn't appear in the top 5 grossing. But when adjusted for inflation, was the highest. Okay, so what I can do there is I can take the top. What I can do is I can take the top movies and sort them by the 3rd column. So 0, 1, 2, 3. I'm going to sort by column 3. Descending equals true. And what I see there is that I actually have Gone with the Wind that was released in 1939. It didn't make a whole lot of grossing dollars, but when adjusted for inflation, made a ton of money. Let's take a look at that. So let's take the top 5 rows from there. And the top 5 all-time adjusted for inflation grossing movies. And now I can bar chart that. So take that, and bar H, title. Oops. Bar H title, I need 2 arguments. Title and gross adjusted, that's column number 3. And here we go. So it turns out that Gone with the Wind, Star Wars, Sound of Music, E.T., and Titanic all made more adjusted for inflation than all of these movies except for Titanic, because Titanic got repeated twice. So even though these movies made a lot of dollars, these movies were still the most popular. All right? Any questions about what we did there? OK, so one thing to note here is that unlike plot, which Luke pointed out previously, bar H does not reorder your categories in order of like biggest to smallest. So for example, here, Titanic made the most grossing. Of these 5, Titanic made the most. But when we plotted them, they just put the movies in the order that they appear in the table. If you wanted to actually make them go from biggest to smallest, which is typically a good thing to do, what you want to do there is you want to take that and you want to sort it before you do the bar H. So before I do the bar H, I want to sort. And then, oops, whoa, that's weird. Sort, and it's running. There it is. Okay. So what I want to do there is before I call bar H, I want to sort it. Now categories would come in the original table. So keep that in mind. Categories appear in order that they. I'm going to show you one more thing, which is right here we were comparing. When we were trying to compare the grossing amount with the grossing amount adjusted for inflation, we kind of had to make 2 plots and kind of like scroll back and forth here. This is not really ideal. What we would like to do instead is kind of put the 2 plots together and see them both in one place. Okay, so to do that, oops, that's not too hard. What I have to do there is when I call bar H, so here's my original gross. Okay, when I call bar H, I can omit the second argument, so I can take it out. And what bar H will do is it will try to make a stacked bar chart, or we're trying to do like a side-by-side bar chart for every column in my original table. So just to remind you, top 5 looks like this. If I do bar H on title, it will say title is my category, and then it will try to plot on the bar chart every other column as a bar. I don't want to plot the studio and the year as a bar. I want to actually only plot these 2 as a bar. So before I can do bar H there, I can select out the columns that I want to plot. So here, I'm going to select out column 0, column 2, and column 3. And now when I do bar H with just title, it will automatically take my title as a column and then plot gross and gross adjusted side by side on the same bar chart. And this is taking its sweet time. Come on. Come on. What happens if I do 1 + 1? Nope. Oh, there it is. Okay, so here what we have is Star Wars: The Force Awakens, gross and adjusted gross. Titanic didn't make as much regular dollars, but made a lot more adjusted dollars. Okay, so very convenient. This bar-ish method allows us to kind of not only plot 1 category and 1 set of numbers, but also plot 2 sets of numbers or 3 sets of numbers or more if you wanted to do that side by side on the same bar chart. Pretty convenient when comparing 2 different variables for different categories. Yes, Emily?
You selected 3 columns, but how come like 5 columns appear in the chart above?
So Emily says, I only selected 3 columns, but why are there 5 guys here? That's because so here is my original table, top 5. And I'm going to select out the 3 columns that I want to plot before I actually plot them. Yeah, so I'm not changing the original table. If I were to try to do bar H title right now, it would error out because it would try to do studio on this bar chart, and then it would fail to do that. Okay, so if I try to do that, it will error, value error, and scroll past all of this and get down to the error. The column studio contains non-numerical values. Okay, so it'll try to do it, and it'll complain when it can't. It contains non-numerical values. Plot cannot be drawn for this column. So you have to select out the columns you want to plot first, and then use bar H to plot them. OK, great question. Any other questions? All right. Got a couple minutes left. I'm going to do one more chart for us. OK, so to kind of lead into what we're going to be doing the rest of this week, we noted here that there are movies, and every movie has a studio. Let's say we want to compare which studios had the most movies. Okay, so how do I find which studios had the most movies? Well, here I have Buena Vista. Buena Vista, Disney made a bunch of movies. Let's see if they were the ones who made the most movies overall. We can do this with a method called group. What group will do is it will create a distribution of categories. Okay, so it will compute for us a distribution of categories. When I do that, I group by studio. What I get is the studio, and then it will go through my entire table, count up however many studios, however many times a studio appeared, and then give me the distribution of studios in this table here. So I have studio as a column, and then count in the second column. It looks like Disney had 29 movies, quite a lot of movies. And now I can take that, and I can save it. Studios. Okay. And as before, I want to sort it first, so it's in descending order. So sort by count. Descending equals true. And then I can do the same thing that I did before, bar H on studio. And voila. It turns out that Disney did not make the most movies, Warner Brothers did. And then came Disney as a close second, or maybe they made the same and it was tied. And then Fox, and then Paramount, et cetera, et cetera, et cetera. And there's some movies here there are some people here that only made like one movie. Okay, cool. So let's go back here. All right, so as Kevin has so kindly mentioned for us before, numerical values in a column does not necessarily mean that the data is numerical. Okay, so because the census example had 0, 1, and 2 in this column for sex, although it had those values, it was not numerical data because those represent categories. It doesn't really make sense to do to take one value from the column and subtract another. Okay, so do be careful when you're working with your data. We consider sex as a categorical column in that case, even though it has numerical values. We've talked about bar H, which displays a categorical distribution. And we do have to make sure that when the variables have some ordering or some fixed size relative to each other, we have to be careful about the way we order the results in this bar H, and we might have different options of visualizations to choose from. But in general, for most categorical data, we can use bar H to kind of compare the counts in different categories. Okay. Finally, we looked at movies, and we looked at how much money each movie made in dollars at the time. We also used like inflation to adjust the number of dollars for today's dollars. And in fact, I saw this little blog post on the Mathematically Literate World. It says, in our world, we say Hollywood breaks box office records with explosions and rising stars. But in the Mathematically Literate world, Hollywood breaks box office records with inflation and rising population. Okay, so it turns out that, for example, in Star Wars 1999, Star Wars 1997, it made more money in grossing, but Darth Vader is greater than Darth Maul. So Star Wars 1977 was better. That's it. See you guys tomorrow.